Okay, so happy birthday, Noga. Where's Noga? So I do recall where I met Noga. It was at Peter Sarnak's house. It was 94 maybe, or 95, something like that. And this young guy walked in and you were talking about, so Peter was asking you why you were signing Neely's name on your papers, and you said because you didn't want to appear trivial, and I thought, oh, what a jerk, he wants his daughter to appear trivial. Tamar was saying that she was excited because she thought that there was this woman who was publishing so much. And for those of us who are not from Israel, I remember when I had my first intern in the lab whose name was Noga, and I expected it to be a man. So, I mean, those of you who are from Israel know that Noga is usually a woman's name, but all of us who are in mathematics and not from Israel just had assumed that it was a man's name. Also, Noga was very significant in one other way. He brought out my competitive instinct. Right, well, he has a competitive instinct too, but I recall it was the beginning of 1997 at the IAS, and Christian and I were trying to figure out how to solve our two-body problem. I had a job in LA and he had a job in Leipzig, and we were commuting, so it was a fairly long commute. We would often meet at the IAS, and that semester we were actually both at the IAS. And we were trying to find jobs together, and you walked into the lounge, we were working on the board, and you asked us if, what we were doing, because we had been talking to various schools, and I told you that we were going to Microsoft, and you just looked at, because for those of you who are younger at that point, Microsoft had no mathematicians, no theoretical computer scientists, no physicists, and you just looked at me and you asked me if I was crazy. And I told you that we would form an amazing combinatorics group, and of course one of the reasons that it became so amazing is that so many of your proteges came and joined, and so many of your colleagues came and visited. So, but I said to Christian, now I really have to come through on this. I want him to eat his words. And so, okay, so I'm going to talk about graphons and machine learning. Okay, so the outline is I'm first going to talk about the general theory of graph convergence and limits for both dense graphs and sparse graphs. And then I'm going to talk about something that we've been thinking about. And we is me and Christian. If any of you don't know, I'm giving the talk for me and Christian, but this is, both of us are wishing Noga a happy birthday. And so I'm going to talk about learning of massive networks. It really surprised us that anyone other than a mathematician actually wanted to use these graphons. Mathematicians seem to like them, which is great, but it seems that data scientists also like them, which was a real surprise to us. Okay, so the motivation is, this agent. So on one side you see a brain cell, and on the other side you see a universe, and you think, wow, these things look kind of similar, and is there one way of talking about massive graphs? So by analogy to thermodynamics as a limit of statistical physics, or differential equations as a limit of an interacting particle system, is there a way of discussing, limits of graphs? And it seemed to us, coming from physics, that of course graph theorists would have done this, and this was the beginning of a long journey. So in 2004, we were with Vera and Latsi and Kadi in that corner lounge, and we said, do graph theorists have graph limits to do large network calculations? We were actually, Christian and I were working with John Huckroft, and we were doing these large network calculations, and we thought, we don't want all the details, we want some kind of a limit. And so this began this very long journey with lots of wonderful mathematics. So it started with an application, but then it just went off into math land. And there were also wonderful other collaborators here, and more recently, some fantastic graduate students, some of whom are related to our older collaborators, like that is young Latsi there. And then in December 2013, I was at NIPS, which is Neural and Information Processing Systems workshop, which is, the big machine learning workshop. And somebody came up to me and said, I'm using your graphons as non-parametric stochastic block models to estimate, actual large networks. And I thought it was a joke, but then it turned out there were lots and lots of people doing this. And so we went back to applications, and then, seeing everybody here who's collaborated with you, my competitive instinct is starting to come out again. And so, somehow in this scenery in the future, we have to find you and do something with you here. There are lots of hard problems here, so we will bring one or more of them to you. Okay, so how do we describe massive networks?
But it's related to property testing.
It's related to property testing, yes, so right there. So questions to be addressed. So we had started off wanting to have something so that, we said, we're sampling the World Wide Web. It's this very large network. We would like to be able to sample, to test some properties. We can't, even do a simple algorithm like PageRank on the entire web. So, if we had a limit, maybe we could find some way to sample, to test properties in a reasonable way. So that was the first motivation. Then the second motivation was, just as you can much more easily sometimes prove something with a differential equation than with an interacting particle system, because you can't see the forest for the trees in the interacting particle system. You're following all of this very detailed behavior, maybe in a similar way, and this turned out to be the case. There are certain things in extremal combinatorics, certain things in phase transitions, which you can prove more easily on the graph than on the graph. And then finally, this surprise that, and this is actually true, at Facebook and at LinkedIn, they are actually using graphons to model the graph. And the people who are estimating like the recommendations on LinkedIn to recommend friends to you are actually using graphons, which is kind of amazing to me. So just because they don't want to overfit, and if they use something with a large number of parameters, they overfit, so they want something smooth to not overfit. Okay, so these are the two things that I'm going to talk about in this lecture. First, the limits, and then a little bit about how you use the limits for estimation of massive graphs. Okay, so, I could look at these three and say which two of the three graphs are more similar to each other, okay? And so this is the same really as asking, is there a good metric? And then if there's a good metric, can I use that to get a notion of metric convergence? And then from all of that, could I somehow generate random graphs once I had a limit object? And can we learn? So these are the questions. And can we learn without revealing things about the individuals on the network? So that'll be the last few minutes of the talk if I get to it. Okay, so overview of what we were, of what's been proved. There are lots of notions of convergence. Now, if you try to go into a new field and think, what does it mean for something to converge? You can always get things to converge, right? I can have a really strong notion of convergence and everything converges to the same point. I can have a really weak notion of convergence and everything converges to a different point. So is there a meaningful notion of convergence that would correspond to what a lot of different people would feel is a good notion? And what made us feel good in this, 2006 through 2012, as we were working on dense graphs, was that we came up with lots of different notions. So notion of metric convergence, and I'll talk more about each of these. Of subgraph frequency convergence, and then because Christian and I are statistical physicists, we started thinking about free energy convergence, which was a more global notion, or other kinds of global notions that computer scientists might care about, like max cut and min bisection. or large deviations with David Gomarnik a few years ago. We came up with that notion. Also, limit objects. So Lotzi and Balazs had shown that you could use a Martingale convergence theorem to get the function to converge, but actually earlier than that, Benjamini and Schramm had looked at convergence of rooted graphs, okay, and so they had a notion of this for sparse graphs, and Aldous and Huxley, even much earlier than that, had talked about infinite exchangeable arrays, a la Kallenberg kind of thing. And so that was also a good notion of a limit. And then more recently, large deviation rates could also be a notion of limit. So there are all these different notions of what the limiting object might be. And then, how do you get a limit? So for dense graphs, the weak Samaretti lemma, which is basically, it was actually done by Fries and Conan, so it's an integrated version, and a compactness argument, or bounded degree graphs, that's just a compactness argument. And for sparse graphs with unbounded degrees, like power law graphs, which is something that's occupied a lot of our time in the past 4 years or so, one of the things that had gotten in the way of doing that was that we needed a different notion of a weak Samaretti lemma, okay, in order to be able to get that, not the standard Samaretti notions. Okay, so here's some notation that's pretty standard, so I'm not going to go through it, but ask me if you don't know what the notation is. Okay, so, and I'll be talking about a few different cases. So there's the random graph, the Erdős-Rényi random graph. Then there's the generalized random graph, which the statistics people and the data scientists call the stochastic block model. So here you can think of case species of particles, IID connecting to each other. And so, red connects to red with probability beta red red. Red connects to blue with probability beta red blue, and there's a p red fraction of red, or p red probability of red, a p blue probability of blue, and so on. So this is just a generalized random graph. And then very different is something like a power law graph. Okay. So here, and I think it might have been Patty who came up with these pictures, but heuristically, what do I want to think about when I think about a graph limit? Okay, I want to take the adjacency matrix of a graph. Okay, so like here's the half graph, and I want to say that whenever there's a 1, I'm going to color it in, and whenever there's a 0, I'm not going to color it in, and then I'm just going to take this limit of the unit on the unit square. So I just get a limit. So that seems really easy, right? So I can do something like a random graph with p equals 1/2. And that converges to the constant function 1/2. The only problem, of course, is that I don't care about the labels. It's up to isomorphism. So, this graph is the same as that graph by relabeling vertices. It's the same as that graph. So all of a sudden you ask, well, what is, so where's the pointer here? Okay, so if you look over there, so why is it that graph and not some other graph? And actually, with Lotzi, Christian and I proved that the limit is unique up to measure-preserving bijection. So the isomorphisms on the left-hand side, on the graph side, turn into measure-preserving bijections on the right-hand side. So it's a big non-uniqueness, but you can talk about modding it out. Okay, so here's some more examples. A randomly grown uniform attachment graph, which goes to this finite thing. A randomly grown preferential attachment graph ordered by degrees. And now we see that this W is unbounded. Okay, it's log X, log Y. So, comparing two graphs. So what is a good notion of a metric to compare two graphs? And here again, we go back to Fries and Conan, and we look at the cut norm of one matrix. Okay, so what this says is, find the max. So I can think of T as complement, and I'm trying to find the max cut in my graph, okay? And now, what I can do if I have two graphs, if they're the same size, I just take the difference of their adjacency matrices. If they're not the same size, I blow them up so that they are the same size. So, if this one has 20 and this one has 30 sites, I take every site here. I'm going to take Louisa comment on, but I'm not going to do that. And I take every site in the one that has 20, and I blow it up 3 times, and I put a complete bipartite graph in there. I take every one that has 30, and I blow it up twice, and I put complete bipartite graphs in there. Now, they both have 60 sites. I take the difference in the adjacency matrices of the two of them. I take the cut norm of that, and then I minimize over all permutations of the vertices because I don't care what the labeling is. Or I could go to the continuum already. I could have a limit, a graphon, and I could look at the cut distance between two graphons, and I could embed the graph in the graphon. So that's what I'm going to do here. So graphon is a symmetric integrable function on the unit square. I mean, later we'll take it to be more than just the unit square because we're going to want a bigger feature space when we're trying to think about real networks. But let's just think about the unit square for now. Then in this same 1999 article, Fries and Kanin had looked at the cut norm of a graphon. So this is, again, just taking the maximum cut. And instead of putting the adjacency matrix there, I put the limit in there. But I'm just thinking about cut. Okay, and then the cut distance between graphons, we know that this is non-unique up to measure preserving bijections. So we minimize overall measure preserving bijections. Okay, now I can embed a graph and a graphon. A graph is just a piecewise constant graphon, right? I can take my unit square, I can divide it up into n squared little cubes. I can say a graph is just something which is constant on each one of those. And then the cut metric does what you would hope it would do. The cut metric, which was defined by taking the difference of the adjacency matrices and taking the cut norm and minimizing over all the permutations, would be the same as the cut norm with the WIJs with the W's in there and minimizing over all measure preserving bijections. Okay, and we say a sequence of dense graphs is metric convergent if it's Cauchy in this metric. Okay, and metric convergence is a wonderful thing to have because, once you have a metric, you can do all kinds of estimates. Okay, so that graph converges, that graph, which is a piecewise constant graphon, converges to that graphon. If the cut metric goes to 0, as n goes to infinity. Okay, so you don't have to read all this, just think about what subgraph frequencies are. Okay, so I can talk about an edge density, I can talk about a triangle density, I can talk about a 4-cycle density, I can talk about a Peterson graph density, okay? And so, the first thing that made us feel like we were really onto something was that for dense graphs, convergence of all subgraphs, okay, edge, triangle, 4-cycle, et cetera, for all finite subgraphs, was the same as Cauchy convergence in the cut metric. Okay, so this says this is a meaningful notion now. And of course, the combinatorialists loved the finite subgraphs because then you could really start to prove something, right? Okay, but being physicists, we're like, no, we got to put statistical mechanics on here. So we said, how about if we put free energies on the graphs, and we have the microeconomical free energies, which said there are a given percentage of red particles, blue particles, green particles, and we have pairwise interactions, and let's say that all of these microeconomical free energies converge. Or computer science. max cuts, min bisections, let's say those converge in all multi-way cuts and bisections. Those are meaningful notions for a theoretical computer scientist. We had something which we called quotients, which were related to summary partitions. And then later with David Marnick, we said, what if we did a large deviation rate corresponding to an entropy where we fixed both the edge and vertex densities and asked how many ways were there of doing this, and the corresponding large deviation rate was the entropy of this graph sequence. And what we were able to prove was that for dense graph sequences, metric convergence is not only the same as subgraph convergence, which I just told you on the last slide, but it's also the same as all four of these global notions. So now, we're really onto something. This is a good notion. There are many, many different things that are the same here, okay? Great. So sparse graphs. Sparse graphs are, so this was with Lotzi and Jeff Kahn, they are much more fragile, okay? So there is no good notion of metric convergence, or at least none that we've been able to find. But when we went back, Benjamini and Schramm, years earlier, had talked about choosing a random vertex and looking at the convergence of the graph rooted at that random vertex, and that turned out to be the same for a sparse graph as these other notions that we had. And so subgraph convergence, which does make sense for a sparse graph, was exactly the same as Benjamini-Schramm convergence, but actually was strictly weaker than, for example, convergence of microcanonical free energies, one of these global notions. And it turns out if you go into, there's a high temperature phase, a low temperature phase. If you're in the low temperature phase, you have counterexamples. It's a strictly stronger notion. Okay, so how about sparse graphs of unbounded degree? So these parallel graphs, Facebook and LinkedIn and the World Wide Web and the Internet and all of these things, these are sparse graphs not of bounded degree like we had just done with Lotzi and Jeff, but unbounded degree. So these are really fragile. And so let's just think about, we kept trying to get counting lemmas and subgraph convergence, but you really have to let go of that. Why do you have to let go of it? It's very, very simple. Let's think of a GNP with p equals n to the minus 2/3. Okay, how many edges do I have? Well, I have n squared times n to the minus 2/3 is n to the 4/3 edges. How many triangles do I have? Well, I have n to the minus 2/3 cubed is n to the minus 2 times n squared cubed, which is n to the 6, which is, right, so n to the minus 2 times n cubed, times n cubed is n. Okay, so I can remove every bloody triangle without changing the edge density. Okay, so, there's no way I'm going to get subgraph. Subgraph convergence for all subgraphs. So we need to let go of some of the fundamental results in dense graph theory. We need to let go of the counting lemma. We need to fundamentally change Semreti's regularity lemma. By the way, the way I describe, you guys don't need to know what Semreti's regularity lemma is, but I now have a great way of describing it to data scientists, which is that in its weak form, what it says is that I can get close to it, that any graph is close in the cut metric, so that's long close in the cut metric, so weakly in the cut metric, to a stochastic block model, generalized Renner, and all these stochastic block models, if I have enough blocks. So in the integrated form, it would be c to the 1 over epsilon squared blocks. In the standard form, it would be a tower, and in a soft and no-giz version, it would be just a mess, but it'd be a lot. But anyway, so it says that graphs are close to stochastic block models. And I told this to an industry conference, Strata, where there are all these people who work at on these big graphs, and they're like, oh my God, why didn't people say that? It's not so complicated. So just tell them any graph is close to a stochastic block model and enough blocks. Okay, so we need new notions, a lot of new notions. So let's first try to do it very naively. Okay, well the problem is that the cut metric is bounded by the one norm, which is just the density of the graph. So for sparse graphs, the density goes to 0. Okay, so yeah, everything converges, it converges to 0. But you want something non-trivial, so you say, okay, well the obvious solution is that I divide through by the density. Okay, and now I'm going to say, I want something to be a Cauchy sequence, you know, when I divide through by the density. So I'm normalizing it properly. Okay, so if I try to do this on the 3 examples that we talked about, the random graph, or the stochastic block model, which is just a generalized random graph, or the parallel graph, the first two, you're going to get a limit which is bounded. The parallel case, you're going to get a limit which is unbounded. Okay? Bolbosch and Reardon, in maybe about 4 years ago or something, did something very nice. They normalized like this, and they said, let us look at graphs which have no dense spots. That is a technical term, but what it means is that basically all parts of your graph are of the same order in n. The density, the edge density in all parts of your graph is on the same order in n. Okay, and then they were able to prove that this kind of normalization worked, it turns out, if the limit is bounded. Okay, it'll correspond to our L infinity case. But let's say that I didn't want to do that. Let's say I wanted to do LP. Let's say I wanted to do parallel graphs. Then the obvious thing is that I want to define a p-norm of the normalized thing where I divided out the density, so I want to put it up or down on the p-norm. Well, just if I put it up or down on that p-norm, which is the 1 norm to the 1 over p minus 1, then that corresponds to a lower bound on the 1 norm, which is the edge density, which says that my graph is dense. So if I'm really naive, then I just get back to dense graphs. So what do I do? And this is what took us a while in working with Henry Cohn and Yufei Zhao. We said, okay, we have 2 inspirations here. First, Samaretti's lemma tells us that I can compare a given graph with a graph averaged over partitions. They're pretty close to each other, okay? And physics, real space renormalization, says I temper singularities by doing some averaging, okay? So, informally, what I want to do is I want to say that a graph is LP upper regular if every partition of the vertices of the normalized graph in which no part is too small is uniform. If I average the graph over these pieces, then I'm going to get something which is uniformly LP bounded. So I take one partition, I do an average, and I take the LP norm, and I look at that. And I take another thing, and I'll tell you in a moment what I mean by no part is too small, but I do this with everything, and there is some uniform upper bound, okay? And then we were able to prove the theorem that we wanted, that for LP upper regular sparse graph sequences of unbounded degree, okay, so these are just the parallel graphs that we're talking about, and many others, of course. Metric convergence is the same as all the global convergence notions, convergence of free energies, of multi-way cuts, quotients of large deviations, okay? So, of course, not of the subgraph frequencies, because we know there are counterexamples there. So let me get a little more precise. So I take a sparse graph and I average it over a partition into q pieces. Okay, and how do I do this? I take all my vertex weights and I add them up. And I take my edge weights and I normalize them by the density of the whole graph. And I properly weight them with the corresponding edge weights at the the vertex weights. So if the vertex weights are all 1, that alpha I, alpha j is not there, and I just get 1 over the size of the partition squared if I have an equal partition. Okay? And so I say that a sequence of graphs is LP upper regular if there's some constant and some eta n going to 0. So what this is telling me is that I want to average over all partitions of order n, of order the size of my graph. And I can have a coefficient that's going to 0 there, so I'm asking for a uniform LP up or down whenever I average over partitions that are of order n. If they're smaller than order n, somebody would call this an exceptional piece, and I'm not going to make you average over exceptional pieces. Okay? And so that was the condition under which we got that theorem that, metric convergence is the same as all the global convergence notions. Okay, so a little more about counting and semi-ready regularity. So we already saw with the triangles and the edges.
What is the role of P? You fix P or it doesn't matter?
It doesn't matter.
And what kind of restriction?
No. I mean, P is between 1 and infinity, okay?
P is between 1 and infinity?
P is between 1 and infinity. I'm going to fix it, and then it will turn out that when it converges, it will actually converge to something which is an L1. It turns out. This isn't obvious, but yeah.
Can one explain what restriction does it give on the graphs, this condition that it's bound?
So, I mean, there are some graphs, and so there are some graphs that we're working on now that Christian's just trying to finish the paper, where they're real. So what this LP is telling you is not like the Bailey and Oliver thing where there are no dense spots. There are definitely things of different orders of n, like with the power law. But there are things which can be much, much sparser than that, which we don't define on a probability space, which we define on a sigma finite measure space, and they're the kinds of things where something grows over time and it leaks out to infinity. We can define graphons for that as well. Those are not going to satisfy this condition. Okay, so if there isn't a way of scaling with n, okay, if there isn't some function that I can scale with n so that I naively would land up with an LP function, then it's not going to be in this space. There are actually some meaningful graphs that have that, even what a physicist would call multi-scale. So let's say it were this power, and then there aren't enough particles in the universe for it to continue to be this power. So it breaks, and it's a different power. And then it breaks, and it's a different power, which is what people find in real-world networks. That won't work here. Okay? So, we also get a modified counting lemma. So it turns out that if your subgraph, if you have simple subgraphs with maximum degree smaller than P, those will converge. Okay? And then a little bit more about the weak regularity lemma. So the Kohei-Kawa and Brutal stuff in the weak form, in the Fries-Common form, would correspond to our L infinity case. And the Bolbosch and Reardon, which they did use in the weak form, corresponds to the L infinity case. Those are like bounded functions. For those of you who know the proof of the weak semi-ready regularity lemma, the proof from the book of the weak regularity lemma, it's an energy increment type of proof. It's a beautiful little proof in which things break up into smaller. So you can do the same kind of proof for L2. I'm cheating a little bit because what happens is that as I take intersections, as I'm iterating and I keep taking intersections of sets, I may get some pieces that are too small and I'm not supposed to pay attention to them according to this notion of upper regularity. They're exceptional in the semi-ready sense. So then I have to deal with those and I lose some constants and stuff. If I get it for p equals 2, then I can get it for the rest of the p's up to p equals infinity by embedding L2. Those go the right way. For p between 1 and 2, actually, interestingly, we get a different number of parts, okay? Instead of constant to the 1 over epsilon squared, you get constant to the 1 over epsilon to the p over p minus 1, so that if p is tending to 1, you're in trouble, okay? So it's a different summary irregularity limit, different scaling for p between 1 and 2. Okay, now I'm going to go in the other direction. So what we got was for both dense and sparse graphs, we've seen that if we have a sequence of graphs that obey certain conditions, either they're dense, which is corresponding to the L infinity case, or they are this LP upper regular, I can get a graphon out of it. Now let's just say that I gave you a graphon, and I said, generate for me random graphs of a certain density, which are consistent with this graphon. What would you do to generate them? I'm just giving you this function on the unit square. Let's say it's LP function on the unit square, and I'm asking generate graphs which would have given me this graphon. Okay? So what do? Well, I take my unit interval, and I just choose n points from it, let's say uniformly at random. Okay, x1 up through xn. Okay? And now what I'm going to do is I'm going to take my w. You remember, I had this function w on the unit square. And I'm going to plug in xi, xj. And those are going to be my candidate edge densities. They're scalable by the right edge density, rho n, and I better make sure that my probabilities don't get bigger than 1, but that's what I'm doing. Okay, so now I just generate random graphs, okay? I've given you this function. You pick n points uniformly at random. I stick them in, w of xi, xj for all the, n choose 2 pairs. I multiply by the density I'm looking for. I make sure it's not bigger than 1. And this gives me, and by the way, I'm talking about drawn from 0, 1, but actually, turns out you can do things in a more general feature space, and you might care about that, because if you're looking at Facebook or something, you might be connecting not just on the basis of something that can be represented on the unit interval. And in fact, with young lots of us, we are looking at what can you tell about the topology of the underlying space from looking at the graphon. So it's kind of interesting, because the topology of the underlying space turns out to be very interesting. But for here, let's just do it on 0, 1. Okay, so now, if I give you a function, I can generate random graphs, and I give you a density, I can generate random graphs which are consistent with that. Okay, and so what we were able to prove is that if W is normalized and rho n goes to 0, but the average density blows up, then this gives you what you hope. This process of generating graphs with these edge densities gives you this graphon. If I then look at a limit of those, I'll get the graphon back. Okay, so now we go in the other direction. And this, takes us to this NIPS conference. Okay, so I'm looking at Facebook today, and I'm saying, what will Facebook look like when it has twice as many members? Okay? And the traditional approach for modestly sized graphs was using what they call the stochastic block model, generalized random graph with k different species. And so they would fit a stochastic block model to the given network. Now, people said to me, those guys don't know what they're doing. They're fitting a stochastic block model. Who says that all networks are stochastic block models? Actually, Samaretti says that all networks are stochastic block models, okay? At least weekly in the cut metric. So it's not such a crazy thing to do. I mean, I don't think these guys based their process on Samaretti, but Samaretti would tell them that was an okay thing to what? Oh, there are some statisticians. You remember their names, Christian, you can look it up. I mean, they're not our community at all. This is like statisticians and applied statisticians, okay? And they really did this. And then they used the estimated parameters. Now, the thing is that as my network is growing, okay, by the way, I've really come to like statisticians all over, so I'm not trying to put them down at all. But it was not the same community, okay? So, yes, and Christian's going to look it up for me right now. I don't remember, but he'll look it up, and then he will pipe up, and then I will pipe up. So, as the number of sites grew, as the number of people on Facebook grows, you better have more and more different species. So K, the number of species, okay, the number of different types of individuals, is growing within, okay? And so what happens is that you land up fitting more and more and more parameters. Okay, Holland, Lasky, and Leinart. Okay? So you land up overfitting, which is why they grasped onto these graphons when they got them, because they said, okay, now let's model our graph. Let's model Facebook as a W-rated graph. Let's estimate an approximation. So that's my graph today. I estimate a graphon approximation to it. You might say, well, it's a function, that's more than it, but it's smooth in some, you might have something smooth in some way so that you don't get this crazy overfitting. And then from that, you could generate a graph that was bigger, but of the same form in some way. And we should recall this theorem, which gives us some hope that this would be a reasonable thing to do. But our task is to estimate an approximation from a single sample. We're not going to be given many samples, because I can't give you tons of Facebooks today to ask you what Facebook is going to look like 2 years from now. I can just give you one. Okay, so can we consistently estimate that? So that's the next step of this. Okay, there's something called the identification problem, which the statisticians, the data scientists also realize, and it has to do with the non-uniqueness. Okay, we know that the graphs that if I have the same specified density, but I generate a set of graphs by just choosing, 1 up to n and plugging them in. If I do that from a W and a W prime, if those are identically distributed, then there must be some third function that they are both measure preserving bijections of. Okay, and it turns out they don't necessarily have to be, there doesn't have to be one function that relates them. There was a mistake in a PNAS article about this, I don't know, 5-6 years ago, that people thought there would be one that they would both be equivalent to, but there were counterexamples to that. And we have a counterexample in our paper. Okay, so graphons should be considered equivalents, what? In our paper, with that forms a counterexample to something which had actually appeared in a PNAS article of some well-known statisticians. Okay, so we should consider them to be equivalence classes of functions. So the goal is, if I have a single observation of a graph, that's Facebook today, I assume that Facebook got generated from some underlying graphon and some underlying density. Okay? And then I want to learn a good approximation to the graphon so that I can then use it to generate random graphs that are consistent of a larger size. Okay? Let's say close in the L2 norm, a least squares fit. Okay? Up to a bijection because there's a non-uniqueness problem. There's also another problem called the alignment problem, which is a huge problem in practice. Okay, so I'm trying to get the same approximation to the real W which underlies Facebook. Okay, so what I want to do is I want to average the adjacency matrix over large blocks. So I get some adjacency matrix, which is some approximation of Facebook today, and I want to average that over a large block. Think kind of testing out different similarity partitions. Okay? And if K events, and this is the number of species, okay, as a function or the number of different colors of my underlying stochastic block model is going to infinity with the number of individuals on Facebook sufficiently slowly, then I'll be able to get something which is a good approximation in L2 norm. The proof idea is that I take these x's that I generated like that and I reorder them and I use concentration. So everything looks very good, except if I happen to be an actual data scientist. Then I see GM, I see Facebook today. But I don't see in my proof the actual xi's that I drew. So I don't know of the vertices. So there's a problem of isomorphisms, and when people are trying to fit these things, they really have this problem, and they do all kinds of ad hoc things to deal with the problem. Okay, and it's a serious problem in practice, and it also means that in general, any algorithm I come up with may be very slow. Okay, so consistent estimation. So the previous work. So there were physicists who just did heuristic clustering. They assumed that there was some kind of underlying clustering that they could discover. Most people who were rigorous didn't want to assume that, so they said, let's make some other assumption, which is also equally ridiculous, like strictly monotone degrees. Well, if you have strictly monotone degrees, it turns out that you can be ordering things according to degrees. Things work out very nicely, and in fact, in our theorems, these existential things, if they're consistent estimators, turn into polynomial time approximations. Everything's very nice in those cases. Then Wolf and Olde in this paper that's like over 200 pages from 2013, which they still haven't published yet, but it was a very nice start to this kind of thing, is they found a block model, they did a reordering that maximized the probability of producing the observed graph, so they did maximum likelihood. And then actually they got consistency according to least squares if it was bounded above. Well, that rules out all parallel graphs. Bounded below, that rules out bipartite graphs, which have zeros in them. And curled or continuous, which actually rules out stochastic block matrices. Nevertheless, it was at least a general theorem. And so our goal is to replace these assumptions by modest integrability conditions. Okay, so here are our results. So what I'm going to do is, A is Facebook today, okay? And I'm going to try to find a K by K block matrix which approximates this. It could be very hard to find because of all the different permutations, but in principle I can do this. And then I'm going to try to look at a least squares approximation and an L2 approximation rather than a maximum likelihood, because maximum likelihood you divide through by things. When you divide through by things, they blow up when you have zeros, which means that you can no longer deal with bipartite graphs, so let's do an L2 approximation. And what we found was we were able to prove that that you can consistently estimate. So what I can do is I can look at Facebook today, okay, and from that I can estimate a function W, okay, and from that function W I can sample. I can use those as my edge weights properly scaled, and I can generate something which will be consistent that I use in the future. Okay, so we don't have good algorithms for doing it. So Abe at Princeton has a polynomial time algorithm for a stochastic block matrix, but we're trying to generalize that to some class of W's. Okay, and now a few minutes of what if we wanted to do this privately. So what if we were taking this seriously and saying, okay, I really want to do this on Facebook, okay? Well, the problem is that for graphs, your edges can reveal a lot of information. For example, in 2009, it was shown that just from who your friends are on Facebook, with very high odds, they can estimate your sexual orientation. You may or may not want to keep that secret, but if you wanted to keep that secret, I can estimate that with very high probability. There are lots of things that can be estimated. Okay, and then people do crazy things like say, oh, I just anonymized the database, I just anonymized the graph. But in fact, in reality, when people try to do this and they release these databases, you can go back in typically and very easily de-anonymize them. So you need a more principled approach. So the more principled approach was to work at al, okay, which is, so I'm going to say that a randomized algorithm is, and this is applied to the case of a network, is epsilon node private if I look at a graph with me and a graph without me, okay? And the probability of any event that I can compute on that graph is not very different with me or without me. Okay, okay, then you don't know very much about me because, you know, you can take me out or have me in and you won't even know, okay? So there's an analogous definition for edge privacy, which is much easier to achieve, which is, you know, pulling out an edge. Of course, I don't really care about an edge. Like, if you pull out the edge between me and Noga, it might still be that the edge between me and Kadi will reveal something. So I'm not as concerned about edge privacy as I am about node privacy, which is, you know, being able to take me out and not tell the difference, okay? So previous work, there's quite a bit on edge privacy for networks, very little on node privacy, mostly dense graphs. So our goal is node private estimation of general, sparse, but so far only bounded graphons, but sparse, okay? Okay, so there's a nice mechanism that Kunal Talwar and Frank McSherry came up with to make the least squares algorithm private. It's a nice estimator. I don't have time to go through it, but it's nice. And we were able to use that and show that we could modify it's a kind of backing off mechanism. So that on arbitrary inputs, it was epsilon node private, so you can't tell if I'm in or out, or to factor 1 plus or minus epsilon. And we get this consistent estimation again. We take Facebook today, we derive from it a W, which won't reveal anything about me being there or not being there. And from that, we can generate other things. Okay, so, everywhere we look, we see massive networks. So here's some of the stuff that was kind of our going into mathematics. So dense graphs. So we have all these different notions of convergence for dense graphs, which we did with Watsi and Kadi and Vera over this very nice period of years. Bounded degree graphs, which Benjamin and Schramm had already looked at, and Aldous and Huxley, in a way, had also looked at. Sparse unbounded degree graphs, which is what we did with Henry Cohn and Yufei Zhao, which we needed to abandon these local notions, come up with a different notion of integrability, let go of the counting limit, except for really, really small subgraphs, and also come up with a similarity lemma on a different number of parts, and then work that, which is madly trying to finish the paper. So there's a question of whether you can get exchangeable sparse graphs, so a version of Aldous Huxley for sparse graphs. And so, why am I saying Huxley? Is something else. Is something else. But Aldous Hoover, excuse me, and different, right? And there were also separate papers, Aldous Hoover. And so that's what we're working on. And Gil was saying, there are things that aren't these LP. And yeah, for example, some of the most common ones would be just if they were different P's, okay? But also very, very sparse. And here what we did was we used a density parameter, and we normalized the weights. So the weights were getting too big. We normalized them by the density parameter, and then let there be a pretty sharp curve. There, what we do instead is that instead of having a probability space, we have a sigma finite measure space. We have Poisson points that go out in that measure space. There are points that there are a lot of disconnected points, which you can think of as the other 6 billion people in the world who haven't yet connected to Facebook. But they've been born, so they were born in this Poisson process. If at some point they form an edge to an existing point, then they get added to the graph. And then what you're doing is, instead of rescaling the height like you do with the density parameter, you are rescaling the underlying space in a way. And so that gives you another set of sparse graphons which are exchangeable and projective. So that's what we're doing with Henry Cohn and Nina Holden, who's she's Scott Sheffield's grad student at MIT. And then we can go the other way, and we can say, let's use non-parametric stochastic block models. And so those are these graphons. What about computability and polynomial time? This is work in progress. with Shanghua Tang and another grad student at MIT. And then could we also maybe do sparse unbounded private estimation? That's more work in progress. And happy birthday, Nova.